We know what a mole is. A mole is a unit, or have you heard, containing 6 times 10 to the 23rd. And now that we know that that value is a mole, we can also figure out that there's this thing called molar mass. So each atom and each compound has to have a certain amount of mass, and we would call that molar mass. More on that in this video. By the end of this video, you'll be able to solve for molar mass of any chemical compound given that molecular formula. Before we jump into molar mass and what it is and how we calculate it, let's have some review first and foremost. What are the 7 diatomic molecules? Hopefully you got them all. They are hydrogen, oxygen, chlorine, fluorine, nitrogen, iodine, and of course, bromine. In the previous lesson, when we talked about the mole, we learned that Avogadro's number, the units thereof, can be used interchangeably with the terms atoms and/or molecules per mole. And if you ever see a question asking you how many molecules or how many atoms, blah, 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 please solve the question, ever, what number should come to your head? That should be Avogadro's number, or the number that represents a mole, and that number would be 6.02 times 10 to the 23rd. So, in chemistry, what unit is commonly used to describe the mass or weight? We don't necessarily talk about all of these elements in terms of pounds. We wouldn't say pounds. So the unit that we use for mass or weight is always going to be grams. So then, what do these numbers on the periodic table mean? All these little numbers at the bottom of each one of these elements. What do they stand for? What do they mean? Hopefully you remember from our periodic table lesson that these small values underneath our atom symbols are literally the mass of the sum of the protons and neutrons. Remember that electrons' mass is negligible. They're so tiny and buzzing around all over the place that their mass doesn't really account for anything in the atom itself. However, when we're thinking about mass for an atom, we are going to add up the protons and neutrons in the center of the nucleus. That's what gives the atom its mass. We call this the atomic mass unit, or AMU, for one atom. So when you see that bottom value for all of these different atoms here, that's the average of all of their isotopes, the protons and neutrons, all added together of naturally occurring variations of these elements. So that's the overall average of one atom of X, Y, or Z would weigh in an atomic mass unit format. So then if every atom on the periodic table has this AMU, this atomic mass unit, this average of what it would weigh, and we know that a mole represents a certain number of atoms, and all atoms have to have mass due to their protons and neutrons, then we can say it's possible to have a certain mass per mole. So in other words, we can have a mass in grams, as we mentioned before, per mole. Yes, that is my depiction of a mole. Again, I don't claim to be an artist, but that's a mole. So then what do we call that? We call that a molar mass in grams per mole. This is the AMU, the atomic mass unit, that mass number on the periodic table. We call that molar mass. Molar mass has units of grams per mole, just as we saw before. So our atomic mass unit, always the small numbers underneath the element symbol, is going to represent a molar mass for one atom of that atom type. And that's literally what molar mass is, which kind of makes sense because there's a molar and there's a mass in grams. So as an example here, how do we figure out the molar mass for an atom on the periodic table? Well, you have to look at the periodic table. And what we just saw from carbon's little tile on the periodic table is that it had a mass of 12.01. And again, that was in grams per mole because there's a molar and there's a mass, a molar mass. So in other words, to make more sense of what this number truly means, is that if we were to weigh out a mole of carbon atoms, So charcoal, what Santa leaves in your stocking when you've been naughty all year. And we were to weigh out a mole of carbon atoms, we would end up having to weigh out 12 grams. So if we weighed out 12 grams, like it is here on this scale, we would know that, hey, that 12 grams, this pile of carbon is literally 1 mole of carbon. That means that in that pile of carbon, there's literally 6.02 times 10 to the 23rd carbon atoms in that pile of carbon. That's kind of cool, isn't it? So let's give it a try. Go ahead and pull out a periodic table or look one up online and figure out what the molar mass in grams per mole of silver is. Make sure you write down this conversion factor of molar mass. A number over another number can always be written as a domino or conversion factor. Make sure you write down the 2 different ways you could write out that conversion factor.
Ready? Go!
Hopefully you went to the periodic table, you found silver, Ag, and you looked for the number underneath Ag. And that number is 107.87 grams per mole. So if we were to weigh out 107.87 grams on a scale of silver, you would have 1 mole of silver present, or you would have 6.02 times 10 to the 23rd atoms of silver if you weighed out 107.87 grams of silver on a scale. So notice that I wrote my dominoes in 2 ways. I have the mole on top and then the grams on bottom are molar mass, or I have the domino flip-flopped and I have the mole on bottom and the grams on top. Remember, these are interchangeable. They mean the same thing. If I write it one way or the other is inconsequential. I can flip my domino piece upside down, backwards, forwards, whatever which way that we need it to be in order for our dimensional analysis problems to work out later. Okay, that's fine and dandy and all, but we don't really come across just a single type of atom very often when we're doing chemistry stuff. Most of the time we end up encountering compounds, so 2 or more atoms together into 1 molecule. So we need to figure out how to calculate the molar mass of compounds. And the way we're going to do this is by adding up the molar masses of every atom that's present in 1 unit of the compound. So for example, in table salt, NaCl, I would look on the periodic table and see that I have 1 Na atom. There's a little invisible 1 there. And each Na atom weighs 22.99 grams per mole. And I have 1 Cl atom, and that 1 Cl atom from my periodic table weighs 35.45 grams per mole. So all I have to do is add these 2 numbers together, and that gives me the molar mass of the compound of salt, NaCl. Need another example? Let's try water. Water is H2O. In this case, we have 2 hydrogens, so I'd have to make sure that I account for both. I have 1.01 gram per mole per hydrogen atom, so I have to have that twice. And then I also have 1 oxygen in a molecule of H2O, and I account for that from the periodic table number for oxygen as 16. If I add 16 plus 1.01 plus 1.01, I get 18.02 grams per mole for the compound of water, H2O. So again, in other words, if I was to weigh out 18.02 grams of water on a scale, I would have 6.02 times 10 to the 23rd molecules of water in that glass. So you're probably going to want to write some of these steps down so you remember how to do molar mass in the future. Step 1 is to multiply the periodic table mass by all of the number of atoms present for each individual atom type. So that's what we did with water. There were 2 H's present, so we had to take our 1.01 and essentially multiply it by 2. That's what I mean by multiply the periodic table mass, that's this guy, by the number of atoms present. That was this guy. Step 2 is to add up each separate atom's mass together. So for the case of H2O, I had to add my H2 and my oxygen together. And step 3 is to never let your number, your final answer that you've worked so hard, go running naked in the streets. No naked numbers. No naked numbers. It's embarrassing. So you have to write your final numerical answer with units of grams per mole so it's not a naked number. Again, if I was to write 18.02 for water earlier, 18.02 what? 18.02 times water has broken up with its X. 18.02 reasons why water is like the most essential chemical on Earth. 18.02 deaths that have occurred in water? Question mark? No, we're not talking about 18.02 what. We have to make sure that we specify with our units present, grams per mole. This is also written as 18.02 grams per mole. Either way is correct. They are equivalent to each other. However, if you get in the habit of writing it this way, it'll make it a lot easier for you in terms of dimensional analysis later. So let's work through this example together. We're going to find the molar mass of acetaminophen, Tylenol, that thing you take when you have a really nasty migraine headache or you've got some pain that you want to go away. Acetaminophen, Tylenol, has a molecular formula of C8H9NO2. So if we were going to find the molar mass of that entire compound, we would first need to find carbon's mass on the periodic table and multiply it by 8 because there are 8 carbons present. Then we would need to find hydrogen's mass and multiply it by 9 because there are 9 hydrogens present. Then we'd look back at our periodic table and find nitrogen's mass, the little numbers underneath nitrogen, and there's only 1 nitrogen present here in this compound, so we would just need 1 of that number. And then we'd look on the periodic table and look for oxygen and find its mass, the small numbers underneath it, and multiply it by 2 because there's 2 oxygen atoms present in acetaminophen. Then we would add all of the values that we gathered together from steps 1 through 4, so we've already done our multiplication, add all those final answers together, and we get a final answer in grams per mole. All right, so then let's work through this one together. Carbon on our periodic table has 12.011 grams per mole. And there's 8 of them. So I would have 12.011 times 8. For hydrogen, we have 1.008 or 1.01 if you want to round for each hydrogen atom present. So that would be 1.008 times 9 gives me what? For nitrogen, nitrogen on the periodic table is right here. It's got 14.007 and there's only 1 of those present. So 14.007 times 1 would just give me 14.007. And finally, oxygen is right here at 15.999. I'm just going to round that up to 16 for the sake of easier math. We have 16 times 2, and what does that equal? So now I can take out my calculator and plug all those into my calculator. So we're going to add this one, with this one, with this one, and with this one all together. What we get is 151.167 grams per mole. Again, the way we can write that is as I've shown here, or for better practice for future dimensional analysis, I'd prefer if you get in the habit of writing it this way so that you know how to use it as a conversion factor later. Think you've got it? Go ahead and pause the video here to try and find the molar mass of sugar, glucose. In 1 molecule of glucose, we have 6 carbon atoms. So I'm going to take my carbon, 12.011 times 6. And then for hydrogen in glucose, I have 12 of those atoms, and per hydrogen is 1.008 grams per mole. So I'm going to take 1.008 times 12. And lastly, we have 6 oxygen atoms in 1 molecule of glucose. So that would be 15.999 times 6. For oxygen, I end up with 95.994. For hydrogen, I end up with 12.096. And for carbon, I've got 72.066. And our final answer after adding all of those together is 180.156. Now that can't just be the only thing you write because otherwise 180.156, what? 180.156 cats? 180.156 dogs? 180.156 times that people get addicted to sugar? What is 180.156? We have to include the units. Otherwise, it's a naked number, and you don't want to send your poor little number out in the streets all naked. So we need to put grams per 1 mole, or 180.156 grams per mole, like that. Either way, they are equivalent. This is preferred. So this is just a heads up for you All of these elements that we mentioned before in our quick review are elements that exist as diatomic molecules. So if I say hydrogen, it's not just an H atom, it's H2. We have to keep this in mind when we're calculating molar mass because we have to essentially double the mass. Anytime we have a diatomic element, we have to expect that there's going to be two of them. Therefore, the mass isn't just going to be for one atom, it would be for two. So keep in mind this can be tricky, you might forget about it, but anytime you see a diatomic element, a diatomic molecule, their molar mass will always be twice the value that's underneath them on the periodic table. Let's give these a try. This will be putting to the test both your molar mass knowledge and your knowledge of being able to write these word chemicals into the formula format, because you won't be able to know how many you need of each until you write it into the formula format first. So go ahead and pause the video here and see if you can answer these 6 questions.
I'm stuck. I'm stuck.
Are you stuck? Let's get you unstuck. Lead 2 sulfate. First, we have to write the ionic formula, the actual molecular formula, before we can solve for the molar mass. Lead is Pb. The 2 stands for +2 charge. And sulfate, 8 is a polyatomic ion. So we need to put SO4, which has a charge of -2. Those two cancel out conveniently. So +2 - 2 gives me 0. Perfect. So my molecule of lead 2 sulfate is PbSO4. Now I can go to my periodic table and find the mass of Pb, find the mass of 1 sulfur, and find the mass of 4 oxygens. All right, so going back to our periodic table now, we can find Pb, peanut butter jelly time, 207.2. There's one of those present, 207.2, plus 1 sulfur atom present, and sulfur is 32.06, plus 4 oxygens. Oxygens right here at 15.99 or 16. 16 times 4. We add all of those together and we get 303.26. Now again, don't ever leave that number alone without its units. That's in grams per mole. How about the molar mass of sodium phosphate? Well, sodium is Na, so we're going to write our Na. And phosphate 8 is a polyatomic ion. So we have a +1 charge for our Na since it's in the first column. And phosphate is PO4 -3 from our polyatomic ions list. We have to drop and swap those guys to make sure our charge is balanced. And we end up with Na3PO4. So we have 3 sodium atoms, 1 phosphorus atom, and 4 oxygen atoms. 1 atom of sodium weighs 23 grams per mole. So 23 times 3 for sodium plus P, phosphorus, is rounded up 31 plus oxygen. There's 16 mass and there's 4 of them. And now let's just add that all up together. And we end up with 164 grams per mole as our final answer for sodium phosphate. What is the molar mass of ethanol? Ethanol, you know that thing in whiskey that gets you real drunk? That's ethanol. Let's figure out the molar mass of ethanol. That is 1, 2 carbon atoms. So carbon is 12.011 times 2 plus hydrogens total. We have 3, 4, 5, 6. So we're going to take our hydrogen value, 1.008 times 6, plus 1 oxygen atom, which is our 16. So then the molar mass of ethanol happens to be 46.07 grams per mole. How about the molar mass for magnesium chloride? Magnesium is here in that +2 column, so Mg +2. And chlorine, is over here in the -1 column, Cl -1. Drop and swap those two together to balance our charges, and we end up with MgCl2. So we have 1 magnesium atom present weighing in at 24.305 grams per mole. And we have 2 chlorines present. Each chlorine weighs 35.45, and there happens to be 2 of them. Adding that all together, we get 95.205 grams per 1 mole. So if we were going to weigh out 95.205 grams of magnesium chloride, we'd have 1 mole of magnesium chloride. So how about some baking soda? What's the molar mass of baking soda, also chemically known as sodium bicarbonate? We have a sodium here, Na, and carbonate, bicarbonate. So we first need to write out the molecular formula for this to figure out how many atoms we have of each. Sodium, we have Na plus 1 from that first column. And bicarbonate is HCO3 whole cookie minus 1. Those two charges balance out. 1 minus 1 is 0. So awesome, we don't have to do any drop and swap there. But now we know how many of each atom we have. We have one Na present, weighing in at 23 grams per mole, plus one hydrogen present, weighing in at 1.008 grams per mole. We have one carbon present, weighing in at a whopping 12.011 grams per mole. And we have 3 oxygens present, each oxygen bringing 16 grams to the table, so plus 16 times 3. And we've got a total 84.019 grams in 1 mole. And last but not least, we have nitrogen gas. Nitrogen is over here on the periodic table, weighing in at 14.007 per atom of nitrogen. Now, don't be fooled here. Nitrogen is one of those diatomic molecules. So it's going to come in pairs. Notice it didn't warn you that. It didn't tell you, hey, remember to multiply by 2. It just said nitrogen gas. So if you didn't remember that that's a diatomic, you would get this answer wrong. Nitrogen gas, diatomic, multiply 14.007 times 2 for the molar mass of nitrogen gas. And we end up with 28.014 grams per mole. If we wanted 1 mole of nitrogen gas, we would weigh out 28.014 grams of it. If you think you've got this concept down pat, make sure you test yourself before you wreck yourself and before you move on to the next topic in chemistry. Make sure you can answer the following question: what is the molar mass of caffeine? The only thing that keeps most of us functioning on a day-to-day basis. What's the molar mass of caffeine? Molecules given to you there. If you'd like to check your answer, please mention that in the comments below and I'll be happy to see if you got it right or not. Or feel free to email me at duckonta@gmail.com if you don't want to make your comment public. If this helped you better understand molar mass and how to find the mass of moles, please give me a quacks up and subscribe to my channel for more educational content and for others like you to find this content and help them too. I hope your day is just splendid and quite ducky. See you later.
No ducks, no glory.